let's have a look at how we can use the principle of mathematical induction to make proofs about divisibility. It is important to note that proofs involving divisibility work a little bit differently to proofs about summations and products and matrices. They kind of all work quite similarly, whereas divisibility does work just a little bit differently, and you'll see that through this. So we're going to look through two examples. The first one we're going to look at is to prove that 4 to the power of n plus 2 is divisible by 3, where n is a non-negative integer. So let's get into it. First thing we always do is talk about the first value, that is when n is 0 here. So p0, that gives us 4 to the power of 0 plus 2. That is equal to 3, which is divisible by 3. Therefore, p0 is true. Second step, we talk about pk, and we always let 4 to the power of k plus 2 be equal to whatever the divisibility number is, so 3 times a, where a is some positive integer. Okay, we've seen that so for the p0, we've seen that a in that case is effectively equal to 1. And it's only going to get bigger than that, so we know it's going to be a positive integer. So that's pk. We've got that let statement there. It is important to use let because we are making that assumption. We're making that that leap there, that we're saying it's true at a certain point along the line. Now we talk about pk plus 1. So 4 to the power of k plus 1 plus 2, that is equal to 4 times 4 to the power of k plus 2. Now we do have a couple of approaches here. I'm going to show you the first method that I went through in class. It is maybe just a little bit less nice than the other way that I'll show you in the second example off to the right there. So we've got 4 times 4 to the power of k, and then plus 2. That 4 to the power of k, we want to turn that into 4 to the power of k plus 2, because that's 3a. We know we want to include that in there, so we're going to put that in. But we've just done a really dodgy thing. All right, we've added that plus 2 inside that set of brackets. So if we're adding something in, we need to take it away as well. Now keep in mind, when we expand that out, we would be getting 4 times 4 to the power of k plus 4 times 2, so plus 8. So we're going to take 8 or take 4 times 2 as well. Okay, that just means that we've got equivalent statements. All right, we're adding something in and taking something out at the same time so that it's all equivalent. Now, that 4 to the power of k plus 2, we've defined that as being 3a. So at this point, we're going to write in 3a, and we're just going to evaluate the mess that we've created off to the right-hand side of this equation. So that's minus 6. It's good practice to say we are using pk at that point. Now, what we're trying to do here is show that pk plus 1, so 4 to the power of k plus 1 plus 2, is equal to 3 times some integer. Okay, so we want to try and pull that 3 out as a common factor. We don't necessarily want the highest common factor, and in fact it's not necessary to have the highest common factor, just 3 as the common factor. Unfortunately, it is. So what that means is pk plus 1 is divisible by 3, so therefore pk plus 1 is true. We probably should say for a minus 2 is a positive integer, since a is a positive integer. Now we just finish off writing the statement that we all love. Since p0 is true, and pk plus 1 is true whenever pk is true, pn is true for all, non-negative integers n. So that's one method that we can use. It is slightly messier in the middle there, but it works, and I know a number of you are happy working with that. Let's look at a slightly alternative method here. This is the method that is presented in the textbook, so you're more than welcome to follow along with this one as well. So Pn is 2 to the power of n plus 2 plus 3n, so 3 to the power of 3n. We're saying that's divisible by 5 for all non-negative integers n. So we're going to follow the same process. P0, the first one, 2 to the power of 2 plus 3 to the power of 3, that's equal to 4 plus 27. That is equal to, sorry, no it isn't. Let's do that right. 2 squared plus 3 to the power of 0, that's equal to 4 plus 1, which is equal to 5. So therefore, P0 is true. Right, 5 is, in fact, divisible by 5. pk, we're going to let 2 to the power of k plus 2 plus 3 to the power of 3k be equal to 5a, where a is some non-negative, in fact, some positive integer. Now we get into pk plus 1. Keeping in mind we need to use pk at some point in here, but let's just write pk plus 1 here. So 2 to the power of k plus 2 plus 1 plus 3 to the power of 3k plus 3. Just notice how I am not just writing it as k plus 3, turning that n plus 2 into k plus 3, and I'm expanding out that 3k plus 3 in there as well. Just trying to keep things as separate as possible, but also make it so that it's really obvious that I've got those original powers still in there. So what that means is then I can use the index laws to make it a little bit nicer and to make it so that it is really clear that we have the values in there. Now at this point we need to be a little bit careful because we do have a couple of different powers in there. There is a little bit going on here. What we really want to try and do is take that pk value and now slot it in. So what we might do is just rearrange that pk. So we might turn it into 2 to the power of k plus 2 is equal to 5a minus 3 to the power of 3k. What this then means is we can substitute it in for one of our powers, and then we're just going to sort of see what falls out afterwards. So we get 2 times 5a minus 3 to the power of 3k plus 27 times 3 to the power of 3k. Now what we want to do next is we really want to try and get 5 out as a common factor. So what I'm kind of seeing here is we've got this set of brackets over here. Let's maybe try and expand that. If we expand that, then we know we're going to get 2 times 5a, which has a factor of 5, and we're going to be able to do something with the 3 to the power of 3k as a pair of like terms. So let's see what happens there when we expand that out. So we get 2 times 5a. Not bothering to evaluate that. One reason why I'm not bothering to evaluate that is that it does prevent me a little bit from just sort of getting into the habit of multiplying by 2. The reason why that's a problem is I could be tempted to do 2 times 3 there, and that's going to really stuff me up. So I'm just leaving it as 2 times 5a. Also, again, I don't need to evaluate that. I know 5 is a factor there. But we are dealing with this business over here. So that has so they are like terms. 3 to the power of 3k is a common factor there. So we get 2 times 5a plus 25 times 3 to the power of 3k. Now we can see really clearly we do have a common factor of 5 in both of our terms. So we get 5 times 2a plus 3 to the power of 3k. We know that 2a plus 3 to the power of 3k is an integer. In fact, it'll be a positive integer since a and k are both positive integers as well. So that means p of k plus 1 is divisible by 5. So we know that when pk is true, pk plus 1 is true. So we just finish off with everyone's favourite statement. Since p0 is true, and pk plus 1 is true whenever pk is true, pn is true for all non-negative integers n. And that is divisibility.